The atmosphere of Earth is the layer of gases, commonly known as air, that surrounds the planet Earth and is retained by Earth's gravity. The atmosphere protects life on Earth by absorbing ultraviolet solar radiation, warming the surface through heat retention, and reducing temperature extremes between day and night. By volume, dry air contains 78.09% nitrogen, 20.95% oxygen, 0.93% argon, 0.039% carbon dioxide, and small amounts of other gases. Air also contains a variable amount of water vapor, on average around 1% at sea level, and 0.4% over the entire atmosphere. Air content and atmospheric pressure vary at different layers, and air suitable for use in photosynthesis by terrestrial plants and breathing of terrestrial animals is found only in Earth's troposphere and in artificial atmospheres. The atmosphere has a mass of about 5.15 times 1018 kilograms, 3/4 of which is within about 11 kilometers of the surface. The atmosphere becomes thinner and thinner with increasing altitude, with no definite boundary between the atmosphere and outer space. The Kármán line, at 100 kilometers, or 1.57% of Earth's radius, is often used as the border between the atmosphere and outer space. Atmospheric effects become noticeable during atmospheric re-entry of spacecraft at an altitude of around 120 kilometers. Several layers can be distinguished in the atmosphere, based on characteristics such as temperature and composition. The study of Earth's atmosphere and its processes is called atmospheric science. Early pioneers in the field include Elie Cousteau and Teichérens de Bort and Richard Assmann. Composition. The three major constituents of air, and therefore of Earth's atmosphere, are nitrogen, oxygen, and argon. Water vapor accounts for roughly 0.25% of the atmosphere by mass. The concentration of water vapor varies significantly from around 10 ppm by volume in the coldest portions of the atmosphere to as much as 5% by volume in hot, humid air masses, and concentrations of other atmospheric gases are typically quoted in terms of dry air. The remaining gases are often referred to as trace gases, among which are the greenhouse gases, principally carbon dioxide, methane, nitrous oxide, and ozone. Filtered air includes trace amounts of many other chemical compounds. Many substances of natural origin may be present in locally and seasonally variable small amounts as aerosols in an unfiltered air sample, including dust of mineral and organic composition, pollen and spores, sea spray, and volcanic ash. Various industrial pollutants also may be present as gases or aerosols, such as chlorine, fluorine compounds and elemental mercury vapor. Sulfur compounds such as hydrogen sulfide and sulfur dioxide may be derived from natural sources or from industrial air pollution. Structure of the atmosphere. Principal layers. In general, air pressure and density decrease with altitude in the atmosphere. However, temperature has a more complicated profile with altitude, and may remain relatively constant or even increase with altitude in some regions, because the general pattern of the temperature-altitude profile is constant and measurable by means of instrumented balloon soundings. The temperature behavior provides a useful metric to distinguish atmospheric layers. In this way, Earth's atmosphere can be divided into 5 main layers. Excluding the exosphere, Earth has 4 primary layers, which are the troposphere, stratosphere, mesosphere, and thermosphere. From highest to lowest, the 5 main layers are: exosphere 700 to 10,000 kilometers, thermosphere 80 to 700 kilometers, mesosphere 50 to 80 kilometers, stratosphere 12 to 50 kilometers, troposphere 0 to 12 kilometers. Exosphere. The exosphere is the outermost layer of Earth's atmosphere. It extends from the exobase, which is located at the top of the thermosphere at an altitude of about 700 kilometers above sea level, to about 10,000 kilometers where it merges into the solar wind. This layer is mainly composed of extremely low densities of hydrogen, helium and several heavier molecules including nitrogen, oxygen and carbon dioxide. Closer to the exobase, the atoms and molecules are so far apart that they can travel hundreds of kilometers without colliding with one another. Thus, the exosphere no longer behaves like a gas, and the particles constantly escape into space. These free-moving particles follow ballistic trajectories and may migrate in and out of the magnetosphere of the solar wind. The exosphere is located too far above Earth for any meteorological phenomena to be possible. However, the aurora borealis and aurora australis sometimes occur in the lower part of the exosphere, where they overlap into the thermosphere. The exosphere contains most of the satellites orbiting Earth. Thermosphere. The thermosphere is the second highest layer of Earth's atmosphere. It extends from the mesopause at an altitude of about 80 kilometers up to the thermopause at an altitude range of 500 to 1,000 kilometers. The height of the thermopause varies considerably due to changes in solar activity. Because the thermopause lies at the lower boundary of the exosphere, it is also referred to as the exobase. The lower part of the thermosphere, from 80 to 550 kilometers above Earth's surface, contains the ionosphere. The temperature of the thermosphere gradually increases with height, unlike the stratosphere beneath it, wherein a temperature inversion is due to the absorption of radiation by ozone. The inversion in the thermosphere occurs due to the extremely low density of its molecules. The temperature of this layer can rise as high as 1,500 degrees Celsius, though the gas molecules are so far apart that its temperature in the usual sense is not very meaningful. The air is so rarefied that an individual molecule travels an average of 1 kilometer between collisions with other molecules. Although the thermosphere has a high proportion of molecules with high energy, it would not feel hot to a human in direct contact, because its density is too low to conduct a significant amount of energy to or from the skin. This layer is completely cloudless and free of water vapor. However, non-hydrometeorological phenomena such as the aurora borealis and aurora australis are occasionally seen in the thermosphere. The International Space Station orbits in this layer, between 350 and 420 kilometers. Mesosphere. The mesosphere is the third highest layer of Earth's atmosphere, occupying the region above the stratosphere and below the thermosphere. It extends from the stratopause at an altitude of about 50 kilometers to the mesopause at 80 to 85 kilometers above sea level. Temperatures drop with increasing altitude to the mesopause that marks the top of this middle layer of the atmosphere. It is the coldest place on Earth and has an average temperature around -85 degrees Celsius, just below the mesopause. The air is so cold that even the very scarce water vapor at this altitude can be sublimated into polar mesospheric noctilucent clouds. These are the highest clouds in the atmosphere and may be visible to the naked eye if sunlight reflects off them about an hour or two after sunset, or a similar length of time before sunrise. They are most readily visible when the sun is around 4 to 16 degrees below the horizon. A type of lightning referred to as either sprites or elves, occasionally from far above tropospheric thunderclouds. The mesosphere is also the layer where most meteors burn up upon atmospheric entrance. It is too high above Earth to be accessible to jet-powered aircraft and balloons, and too low to permit orbital spacecraft. The mesosphere is mainly accessed by sounding rockets and rocket-powered aircraft. Stratosphere. The stratosphere is the second lowest layer of Earth's atmosphere. It lies above the troposphere and is separated from it by the tropopause. This layer extends from the top of the troposphere at roughly 12 kilometers above Earth's surface to the stratopause at an altitude of about 50 to 55 kilometers. The atmospheric pressure at the top of the stratosphere is roughly 1/1000th the pressure at sea level. It contains the ozone layer, which is the part of Earth's atmosphere that contains relatively high concentrations of that gas. The stratosphere defines a layer in which temperatures rise with increasing altitude. This rise in temperature is caused by the absorption of ultraviolet radiation from the sun by the ozone layer, which restricts turbulence and mixing. Although the temperature may be -60 degrees Celsius at the tropopause, the top of the stratosphere is much warmer and may be near 0 degrees Celsius. The stratospheric temperature profile creates very stable atmospheric conditions, so the stratosphere lacks the weather-producing air turbulence that is so prevalent in the troposphere. Consequently, the stratosphere is almost completely free of clouds and other forms of weather. However, polar stratospheric and aqueous clouds are occasionally seen in the lower part of this layer of the atmosphere where the air is coldest. This is the highest layer that can be accessed by jet-powered aircraft. Troposphere. The troposphere is the lowest layer of Earth's atmosphere. It extends from Earth's surface to an average height of about 12 kilometers, although this altitude actually varies from about 9 kilometers at the poles to 17 kilometers at the equator, with some variation due to weather. The troposphere is bounded above by the tropopause, a boundary marked in most places by a temperature inversion, and in others by a zone which is isothermal with height. Although variations do occur, the temperature usually declines with increasing altitude in the troposphere because the troposphere is mostly heated through energy transfer from the surface. Thus, the lowest part of the troposphere is typically the warmest section of the troposphere. This promotes vertical mixing. The troposphere contains roughly 80% of the mass of Earth's atmosphere. The troposphere is denser than all its overlying atmospheric layers because a larger atmospheric weight sits on top of the troposphere and causes it to be most severely compressed. 50% of the total mass of the atmosphere is located in the lower 5.6 kilometers of the troposphere. Nearly all atmospheric water vapor and moisture is found in the troposphere, so it is the layer where most of Earth's weather takes place. It has basically all the weather-associated cloud genus types generated by active wind circulation, although very tall cumulonimbus thunderclouds can penetrate the tropopause from below and rise into the lower part of the stratosphere. Most conventional aviation activity takes place in the troposphere, and it is the only layer that can be accessed by propeller-driven aircraft. Other layers. Within the 5 principal layers that are largely determined by temperature, several secondary layers may be distinguished by other properties. The ozone layer is contained within the stratosphere. In this layer, ozone concentrations are about 2 to 8 parts per million, which is much higher than in the lower atmosphere, but still very small compared to the main components of the atmosphere. It is mainly located in the lower portion of the stratosphere from about 15 to 35 kilometers, though the thickness varies seasonally and geographically. About 90% of the ozone in Earth's atmosphere is contained in the stratosphere. The ionosphere is a region of the atmosphere that is ionized by solar radiation. It is responsible for auroras. During daytime hours, it stretches from 50 to 1,000 kilometers and includes the mesosphere, thermosphere, and parts of the exosphere. However, ionization in the mesosphere largely ceases during the night, so auroras are normally seen only in the thermosphere and lower exosphere. The ionosphere forms the inner edge of the magnetosphere. It has practical importance because it influences, for example, radio propagation on Earth. The homosphere and heterosphere are defined by whether the atmospheric gases are well mixed. The surface-based homosphere includes the troposphere, stratosphere, mesosphere, and the lowest part of the thermosphere, where the chemical composition of the atmosphere does not depend on molecular weight because the gases are mixed by turbulence. This relatively homogeneous layer ends at the turbopores found at about 100 kilometers, which places it about 20 kilometers above the mesopores. Above this altitude lies the heterosphere, which includes the exosphere and most of the thermosphere. Here, the chemical composition varies with altitude. This is because the distance that particles can move without colliding with one another is large compared with the size of motions that cause mixing. This allows the gases to stratify by molecular weight, with the heavier ones, such as oxygen and nitrogen, present only near the bottom of the heterosphere. The upper part of the heterosphere is composed almost completely of hydrogen, the lightest element. The planetary boundary layer is the part of the troposphere that is closest to Earth's surface and is directly affected by it, mainly through turbulent diffusion. During the day, the planetary boundary layer usually is well mixed, whereas at night it becomes stably stratified with weak or intermittent mixing. The depth of the planetary boundary layer ranges from as little as about 100 meters on clear, calm nights to 3,000 meters or more during the afternoon in dry regions. The average temperature of the atmosphere at Earth's surface is 14 degrees Celsius to 15 degrees Celsius, depending on the reference. Physical properties. Pressure and thickness. The average atmospheric pressure at sea level is defined by the International Standard Atmosphere as 101,325 pascals. This is sometimes referred to as a unit of standard atmospheres. Total atmospheric mass is 5.148 times 1,018 kilograms, about 2.5% less than would be inferred from the average sea level pressure and Earth's area of 51,007.2 megahectares, this portion being displaced by Earth's mountainous terrain. Atmospheric pressure is the total weight of the air above unit area at the point where the pressure is measured. Thus, air pressure varies with location and weather. If the entire mass of the atmosphere had a uniform density from sea level, it would terminate abruptly at an altitude of 8.50 kilometers. It actually decreases exponentially with altitude, dropping by half every 5.6 kilometers or by a factor of 1 every 7.64 kilometers. The average scale height of the atmosphere below 70 kilometers. However, the atmosphere is more accurately modeled with a customized equation for each layer that takes gradients of temperature, molecular composition, solar radiation and gravity into account. In summary, the mass of Earth's atmosphere is distributed approximately as follows: 50% is below 5.6 kilometers, 90% is below 16 kilometers, 99.99997% is below 100 kilometers, the Kármán line. By international convention, this marks the beginning of space where human travelers are considered astronauts. By comparison, the summit of Mt. Everest is at 8,848 meters. Commercial airliners typically cruise between 10 kilometers and 13 kilometers, where the thinner air improves fuel economy. Weather balloons reach 30.4 kilometers and above, and the highest X-15 flight in 1963 reached 108.0 kilometers. Even above the Kármán line, significant atmospheric effects such as auroras still occur. Meteors begin to glow in this region, though the larger ones may not burn up until they penetrate more deeply. The various layers of Earth's ionosphere, important to HF radio propagation, begin below 100 kilometers and extend beyond 500 kilometers. By comparison, the International Space Station and Space Shuttle typically orbit at 350 to 400 kilometers within the F layer of the ionosphere, where they encounter enough atmospheric drag to require reboosts every few months. Depending on solar activity, satellites can experience noticeable atmospheric drag at altitudes as high as 700 to 800 kilometers. Temperature and speed of sound. The division of the atmosphere into layers, mostly by reference to temperature, is discussed above. Temperature decreases with altitude starting at sea level, but variations in this trend begin above 11 kilometers, where the temperature stabilizes through a large vertical distance through the rest of the troposphere. In the stratosphere, starting above about 20 kilometers, the temperature increases with height, due to heating within the ozone layer caused by capture of significant ultraviolet radiation from the sun by the dioxygen and ozone gas in this region. Still another region of increasing temperature with altitude occurs at very high altitudes, in the aptly named thermosphere above 90 kilometers. Because in an ideal gas of constant composition the speed of sound depends only on temperature and not on the gas pressure or density, the speed of sound in the atmosphere with altitude takes on the form of the complicated temperature profile, and does not mirror altitudinal changes in density or pressure, density and mass. The density of air at sea level is about 1.2 kilograms per cubic meter. Density is not measured directly but is calculated from measurements of temperature, pressure and humidity using the equation of state for air. Atmospheric density decreases as the altitude increases. This variation can be approximately modeled using the barometric formula. More sophisticated models are used to predict orbital decay of satellites. The average mass of the atmosphere is about 5 quadrillion tons, or 1,200,000th the mass of Earth, according to the American National Center for Atmospheric Research. The total mean mass of the atmosphere is 5.1480 times 1,018 kilograms, with an annual range due to water vapor of 1.2 or 1.5 times 1,015 kilograms, depending on whether surface pressure or water vapor data are used, somewhat smaller than the previous estimate. The mean mass of water vapor is estimated as 1.27 times 1,016 kilograms, and the dry air mass as 5.1352 plus or minus 0.0003 times 1018 kilogram. Optical properties. Solar radiation is the energy Earth receives from the Sun. Earth also emits radiation back into space, but at longer wavelengths that we cannot see. Part of the incoming and emitted radiation is absorbed or reflected by the atmosphere. Scattering. When light passes through Earth's atmosphere, photons interact with it through scattering. If the light does not interact with the atmosphere, it is called direct radiation and is what you see if you were to look directly at the Sun. Indirect radiation is light that has been scattered in the atmosphere. For example, on an overcast day when you cannot see your shadow, there is no direct radiation reaching you. It has all been scattered. As another example, due to a phenomenon called Rayleigh scattering, shorter wavelengths scatter more easily than longer wavelengths. This is why the sky looks blue. You are seeing scattered blue light. This is also why sunsets are red. Because the sun is close to the horizon, the sun's rays pass through more atmosphere than normal to reach your eye. Much of the blue light has been scattered out, leaving the red light in a sunset. Absorption: different molecules absorb different wavelengths of radiation. For example, O2 and O3 absorb almost all wavelengths shorter than 300 nanometers. Water absorbs many wavelengths above 700 nanometers. When a molecule absorbs a photon, it increases the energy of the molecule. This heats the atmosphere, but the atmosphere also cools by emitting radiation, as discussed below. The combined absorption spectra of the gases in the atmosphere leave windows of low opacity, allowing the transmission of only certain bands of light. The optical window runs from around 300 nanometers up into the range humans can see, the visible spectrum, at roughly 400 to 700 nanometers, and continues to the infrared to around 1100 nanometers. There are also infrared and radio windows that transmit some infrared and radio waves at longer wavelengths. For example, the radio window runs from about 1 centimeter to about 11 meter waves. Emission is the opposite of absorption. It is when an object emits radiation. Objects tend to emit amounts and wavelengths of radiation depending on their blackbody emission curves. Therefore, hotter objects tend to emit more radiation, with shorter wavelengths. Colder objects emit less radiation, with longer wavelengths. For example, the Sun is approximately 6000 K. Its radiation peaks near 500 nanometers, and is visible to the human eye. Earth is approximately 290 K, so its radiation peaks near 10,000 nanometers, and is much too long to be visible to humans. Because of its temperature, the atmosphere emits infrared radiation. For example, on clear nights Earth's surface cools down faster than on cloudy nights. This is because clouds are strong absorbers and emitters of infrared radiation. This is also why it becomes colder at night at higher elevations. The greenhouse effect is directly related to this absorption and emission effect. Some gases in the atmosphere absorb and emit infrared radiation, but do not interact with sunlight in the visible spectrum. Common examples of these are CO2 and H2O. Refractive index. The refractive index of air is close to, but just greater than 1. Systematic variations in refractive index can lead to the bending of light rays over long optical paths. One example is that, under some circumstances, observers on board ships can see other vessels just over the horizon because light is refracted in the same direction as the curvature of Earth's surface. The refractive index of air depends on temperature, giving rise to refraction effects when the temperature gradient is large. An example of such effects is the mirage circulation. Atmospheric circulation is the large-scale movement of air through the troposphere, and the means by which heat is distributed around Earth. The large-scale structure of the atmospheric circulation varies from year to year, but the basic structure remains fairly constant because it is determined by Earth's rotation rate and the difference in solar radiation between the equator and poles.